thanks for joining the session. The session is going to be jointly spoke by me and Wenwen from NVIDIA, and I think we can get straight in. So quick intro of myself. My name is Aiden. I'm one of the co-founders and CTO at TwelveLabs, and today I'm going to talk about video understanding and a training recipe for one of our models, Maringo, which is a native video native embedding model, and go over that together with you. So before we go into that, I wanted to give you a quick intro of our company, of my startup. We are TwelveLabs. We are a global full-stack video understanding research and product company. So we work with lots of videos. We also do full-stack research and product, which means we do both model training, deployment, and also product building available via APIs. And we're headquartered here in San Francisco with Seoul office and global offices around the world. So we try to build world-leading video foundation models, which I'm going to get into details. We're extremely privileged to work with some of our amazing clients. Our clients are major sports leagues, world-leading content creators, the world's biggest security companies, and M&E studios and broadcasters. And one of them I want to highlight today is MLSE, Maple Leaf Sports Entertainment. For those of you who doesn't know, MLSE is the owner of the Toronto Raptors and Toronto Maple Leafs, the teams. And they essentially have decades of raw footage of their players, games, and practice sessions, highlights in their archive where they want to create new contents for better fan engagement. And I'm going to talk about them more in details later in my slide. We are also a Series A company. We have raised $107 million in total. NVIDIA is one of our partners, Wenwen. Here's to talk about how we work together closely. They help us build and train more efficient video language models. We're also, amazing partner, Databricks. They power our GPUs and training infrastructure. Their training platform is extremely easy to use. So for those of you who haven't tried it out, it's awesome. So try it out. Please try it out. And we are SOC 2 compliant. We're an enterprise SaaS software company. We are a team of 60+ scientists and engineers who marries video and language. Our team previously achieved many wins over the last 10 years in language and video understanding areas. One of the wins that I'm proud of is ICCV Value Challenge in 2021, which was one of the first video search competition hosted by Microsoft and ICCV. And we were able to win the first place here. One of the things that I want to highlight because when we participated, we used the perks from our participating in an accelerator, Techstars accelerator, and we were able to win against tech giants. Again, I'm very proud to be part of this team, scientists and engineers. These exceptional team members make our jobs and our mission possible. So enough of our company. Going deep a little bit into video understanding. So why does video understanding matter? It's because we believe video is the language, everyone's first language. Think about your first memory. You're not picturing words. It's more like you're replaying a part of your life, almost watching a video, right? It's the best data format. Video is the best data format that accurately represent our physical world. This is why video has become the dominant mode of preserving knowledge today. And it's also called world data these days. So with the improvements in technologies to film, stream, and store videos, as a matter of fact, the video would explode in every industry, taking up 80 to 90% of the world's entire data. And that's why understanding video is going to be more and more important. So what are we trying to solve here? Let's say you're a company, or let's say you have an archive of your favorite team, all the videos in the world of your favorite team or players. What kind of questions you want to ask to this archive of videos, right? If you're a huge fan of San Francisco 49ers, for example, for me, I would ask something like, show me all the scenes where Jerry Rice, the legend from 49ers, scored a touchdown against Seahawks. or something like a dry one, something like tell me key moments that happened on a particular date. So given this archive, this kind of operation is exactly what you want to do, because then you can you will be able to use the retrieved contents in your business in the context of your business. But how many of you have been actually frustrated with zero result when you type in similar queries or search queries in Google Drive or your gallery, right? You don't really get results these days, and it's wasting lots of valuable video assets because you're not able to find and understand them. And one of the core reasons is because these retrieval nowadays is reliant on tags, and tags doesn't work because when you submit a query, when you submit an instruction that you want to find, it's not the tag itself does not match to that instruction. So, and these manual tagging is usually labor intensive. They're inconsistent and not very effective on retrieving the contents that you want to find. So but in going fast forward to 2020, 2021, new technology paradigm has emerged, languages interface. In 2021, everybody knows the first GPT-3 model came out. It gave a segue to interact with text data through language. Clip model in 2021 gave a segue to interact with image data with language. For us, we want to see what can we create a language interface for videos. So we trained and deployed two video language models. We call it Maringo and Pegasus. Maringo is a video embedding model that turns video into embeddings, essentially enabling archival video search. Video language model takes in a video as a prompt, and able to perform question and answering on top of that. And with these two models, we believe video understanding can be solved together. Quick demo of what we do. Using these two embedding models, you can submit semantic text queries. Something like receiver catches deep ball for touchdown, is able to retrieve it instantly. Charlie Chaplin attempting to walk down escalator in vain. These are all queries that you're able to submit on an archive of video without having to think about what tags you have used earlier when you upload these videos. You're also able to generate summaries, so video to text operations. Able to get highlights, so getting both timestamp and chapters, and simpler description as well. And today, I want to focus on the first model, our Maringo model, and walk through how we, at the high level, how we trained this model. Before we go into the training part, I want to share insights on what makes video understanding really challenging in technology perspective. Right? If you look at this image, it can be both sunset or sunrise. You don't have an idea. If just by looking at this image, you're not able to assess that. But through videos, you're able to clearly see that because video in itself is a multiple frames where it has temporal components inside as a native nature of the video, right? So temporal understanding is one of the considered core parts of the video data. There's also audio components. Sorry, the audio is not being shared here. But depending on what kind of music is being submitted into the video, the impression of that video can be very different. One can feel it's a very sorrow video or sad video. The other can be very exciting video if you put in party-like music into the video. So another consideration that video understanding has is audio understanding. Third is to align these video data, this continuous video data with text data. So with this video data that's very continuous, it's audio-visual data that's very continuous, you have to align that to text data. For example, if you want to ask questions like where and when is this video taken, you need to train the model so that this video, you have to close the gap between the modality, these two modalities. So modality alignment is another challenge that the model faces. So these three challenges are very specific to the models, but there are also engineering challenges that needs to be considered. This is a screenshot that I took from the Databricks website. The most powerful node, P5 instances, it's composed of 800 GPUs, has roughly around 25 terabytes of local storage. And this will be enough for training very large language models because I'm just taking this from the Llama 4 model, which is trained on Llama 30 trillion tokens in FP8. Roughly, that's around 25 to 30 terabytes, which can fit into this single node of local storage of 25 terabytes. For videos, on the other hand, if you want to train your model on 50 million hours of video, that's roughly 5 petabytes of video files, 150x of the storage you need compared to language model. So another axis apart from the model is that engineering-wise, there's a huge data scale challenge that you need to solve. So with these four challenges in your mind, how do we train video native embedding models? Our intuition was to start from CLIP model, which is image language model, which many of you already know, right? CLIP is composed of two components. One is a text encoder that takes in text and translates to embedding. Image encoder that translates image to embedding. It's trained to align these two modalities by making positive, relevant image text pairs closer to each other and negative, irrelevant image text pairs further from each other. It's contrastive loss, trained on very large scale image text pairs. Now, in order to expand this CLIP model to videos, I'll go one by one from the left to right, from data layer to model layer to the training layer, to show you what needs to be done. So first, in the data layer, to expand to videos, instead of image to text pairs, we need an equivalent set of high-quality video text pairs to train the model. And so what does high-quality video text pair mean, though? Right? We can take some learnings from a CLIP model. There's been various scaling law report being shared on CLIP model. What makes a very good what is the scaling law for a CLIP model? So scale definitely matters for video text pairs as well. So we need lots of data. Composition of these video text pairs also matter a lot. If you're not familiar with data comp challenge, it's a challenge designed to assess the composition of the image text pairs. So given a fixed budget of compute and number of data, the challenge is to let the participants change how these image text pairs are composed within that fixed budget. And recent studies have shown it could, depending on how you compose it, the accuracy can vary up to 10+%. So composition of video text pairs will matter too. Lastly, the quality of these text descriptions will matter a lot. For example, given the same image, it's one thing to explain it in one sentence, in a very high level, and another to describe it in details, almost in paragraph. So the same will apply for high-quality video text pairs. So with these three factors or learnings from CLIP in mind, what we did is just apply the same learnings in video text pairs, right? We first acquired lots of data. So we started from a huge video text corpus, whether it's publicly available or privately licensed. So that's the scale part. We filtered it to 100 million video text pairs through various techniques. Here, we are thinking about that composition of video text pairs, how we're going to compose that 100 million video text pairs. And then we recaptioned it, basically rewriting the text pairs to models or human annotators to augment the existing 100 million video text pairs. And our final data set composition is basically a combination of these three of video text pairs, image text pairs, and audio text pairs all together to train truly multimodal video embedding model. And in this process, NVIDIA has a tool called NeMo Curator, which accelerates the video processing significantly. If you haven't checked it out, I strongly recommend to try it out. It uses GPU to process these videos and perform captioning or filtering operations on top of it. So this is something that we have closely worked with the NVIDIA team to when we constructed our data pipeline. Next is the modeler, text encoder. We're still going to use text as the interface, so we don't have to modify that one. But we do need to change the image encoder because Clip's image encoder does not have the temporal understanding, and it does not consider the temporal understanding and audio understanding part, which are both inherent nature of video. So we designed a new model architecture that can do that, composed of 3 parts. First, a vision encoder that can take in multiple frames and map temporal relationship between the frames instead of a single frame vision encoder. An audio encoder that captures both non-speech and speech semantics. And fusion model that fuses the 2 modalities to come up with a final multimodal embedding that captures both audio and visual representation of a video. So we modified that Clip's image encoder into video native encoder, trained on top of large-scale video text pairs. And it's being trained on the same training objective, which is to make positive or relevant video text pairs closer to each other and make irrelevant negative video text pairs farther to each other, basically contrastive laws. Trained on top of a few hundred H100s, Databricks H100 plus NVIDIA cluster, GPU cluster on top of it, to make the training process really efficient. And our results, I'm not talking about the Pegasus layer right now, but Marengo, compared to Google's multimodal embedding, Vertex API, or OpenAI's Clip, we have the state-of-the-art results. We also evaluate in various aspects, not just on single benchmark, visual search, motion search, small object search, image search. All these aspects together evaluate on 72 different evaluation data set together and got state-of-the-art results. And through this video embedding model, now what you can do is to run these sort of semantic text queries on an archive of videos. So something like Spider-Man flies through a street and catches a car with his web, or even submit an image query, like finding a logo, finding a moment where certain logos appear semantically without having to extract logo from separate expert models. I haven't touched upon the Pegasus, the video language model too much, but Pegasus model essentially is to turn your unstructured video data into text so that you can perform question answering on top of these videos. And the reason why this Pegasus layer is also important is when you think about the original problem of having 1,000 hours or 1,000,000 hours of video database, and if the user wants to submit a prompt, something like show me all the scenes where Jerry Rice from 49ers scores a touchdown against Seahawks, you essentially want an answer machine that can answer this, right? Something like in video A from October 20th in 1994, Jerry scores 4 touchdowns. Or in video B, 2 touchdowns were scored at this moment and this moment, right? And if you're familiar with RAG, RAG workflow for text, this is essentially RAG for videos, right? You're trying to do retrieval first, getting the top K candidates, and based on that top K candidates, the video language model answer to that user prompt. So this is essentially what we want to build. So 2 components, video embedding model, video language model that enables RAG workflow for videos. And through this pipeline, MLSC, again, one of our customer, they achieved 98% efficiency in highlight creation. They're able to quickly find and retrieve the right moments for them to create contents from their archive. That took 16 hours to 9 minutes. So, conclusion, videos right now, it takes 80% of the data, but the utility is close to 0 because you can't find them and you can't understand them. Still, video understanding is still unsolved science and engineering problem. We've made good progress, but lots of progress needs to be made. And we believe, TwelveLabs, we believe strong video embedding and language model with this system are fundamental blocks to solve them. So if you're interested in solving this problem together, we're actively hiring. So feel free to send me a note. Thanks.